I will give a quick revision about Chapter 2. Chapter 2, we are going to start with the definition of the torque. What is torque? But before that, let's remember what is point mass of an extended object. Remember, we said that an object can perform two basic types of motion. One of them is the translational motion, the other one is rotational motion. And if object sentence talks about the translational motion of the object, we are going to treat object as a point mass. If the motion of the central mass of object is described, that motion is called translational motion. And when translational motion of the object is studied, and the sentence is talking about translational motion of the object, we are going to treat this object as a point mass. And we said that three keywords talks about translational motion. What are they? Revolve, orbit, and to travel. Revolve is about circular motion. Orbiting is about also circular motion. It's a kind of translational motion. Travel can be used also for circular motion or any type of motion, which is going to go on a path, straight path, or a curved path, we don't care. So when a sentence is done by these three keywords, we are going to treat object as a point mass. Trading, you are saying trading. In fact, object is not point or extended, but we are trading it like this. It's a consideration. Okay. Two examples about that. Earth revolve around the sun. So it defines circular motion. It's a kind of translation motion. You should treat Earth in this case point mass. Or moon is orbiting the Earth. Or car is moving, traveling in a circular path. In all these two examples, we are defining translational motion. Object is changing position from one point to another to another, which you have to treat object as a point mass. But there's another type of motion, which is named as rotational motion. If the rotational motion of the object is studied, in this case, we have to treat object as extended object. And again, three keywords. Always talks about, two of them talks about rotational motion, rotating and spinning. Rolling is a different types of motion, which is about rotation and also translation. However, in rolling cases, also we have to treat object as an extended object because every single point on the rolling object will have different velocity. That's why you should treat it as extended object. Logic was this. When you are describing the motion, studying just one single motion is enough to describe the whole object's motion. We say treat object as a point mass. But if you are studying an motion, you have to study every single point on the object as one by one. So we say it's extended object. Rolling cases and rotating or spinning cases, we have to treat object as extended object. And these words define rotational motion, so you should treat object as extended object. And then definition of the torque. So this chapter is mostly about rotational motion. So first we have to think about or study about what causes the rotation. How can we rotate an object? You can translate an object by force. Everybody knows that. If you apply some net force on an object will start translating from one point to another. Best example is the car. You are pushing the gas, so the car starts to move. So this is what translational motion. But rotational motion needs another quantity, not only the force. Force is not enough quantity for making the rotation. Torque causes the rotation, or torque starts the rotation of an object. So that's why its definition is so clear. It's about rotation. Look at that. Torque is a quantity that measures ability over force to rotate an object. So then we can say that ability over force to rotate an object. So some forces can able to rotate an object, which means some force may not cannot able to rotate the object. So then we are going to study these cases. And this definition, of course, must be known. So every definition is potential distribution, as I said to you. So it is a quantity that measures ability over force to rotate an object. It's called torque. So what is this ability? How a force is able to rotate an object, or what forces are unable to rotate an object? Now we will talk about these things. A force is able to rotate an object if it produces some torque, and a force is unable to rotate it if it does not produce a torque. Cases. If the force acts on an object at some distance away from the axis of rotation, perpendicularly, this force produces a torque. But if a force acts at the axis of rotation, like this, look at that, F1 is acting on axis of rotation, or if a force acts on an object so that its extension passes through the axis of rotation, these two forces cannot produce a torque. Then, all other cases, there is some torque. Two cases cannot produce a torque. If a force acts on axis of rotation, or if a force extension passes through the axis of rotation, these two forces cannot produce a torque. Any other force acting on the object will produce some torque. For example, this one. Will it produce some torque? Let me check. Extend it. When you extend, say that F3, when you extend it, if it's not passing through the axis of rotation, it produces some torque. Maybe big, maybe small, but it produces some torque. Okay? Then, by the time this distance, perpendicular distance to the force from the axis of rotation is given in a linear arm. The perpendicular distance from the axis of rotation to a line along the direction of the force is called linear arm. This definition is minimum 4 times, as on the street. According to that definition, I can draw a linear arm. First, let's say that a perpendicular distance from where? From the axis of rotation. So where is the axis of rotation? We are going to start from here. Distance from axis of rotation to a line, another line. But this line is through what? Through the force. You are going to draw a line along the force. Let's draw it. Is the line along the force? Yes, it is. Is it vertical? Yes, it is. Then you are going to start the line from axis of rotation. It will be perpendicular to that. So, how can you draw a perpendicular line to a vertical line? Vertical and horizontal perpendicular to each other. So you are going to draw a horizontal line. This horizontal line is going to be the gram for this force. That is the gram. For other force, you are going to draw a line along the force, then start a line from axis of rotation until that line, what must be perpendicular. This is also lever arm. Lever arm is not always equal to length of the object. Test one question. The most incorrect answer to the question was this. So many of students, because my wrote here is 1 meter, it was in the middle. Many students write 1 meter as a lever arm, but it was in the middle. If it is in the middle, what happens to the lever arm? Lever arm is going to be half. Yani 1 divided by 2 or 0.5. Yani you should be careful about this. Length of the object is not always the lever arm. You have to draw a line along the force. Then you are going to start distance from axis of rotation until this line perpendicular is lever arm. Or lever arm for that one. Not start from here. It will start from where? Axis of rotation. Until where? The line along the force. Okay. This is how we define the lever arm. And then you'll learn that to produce torque, we need 2 things. Absolutely force. Without force, no torque. But not enough. And also you need lever arm. Force must act over a lever arm. When we have these 2, force and lever arm for that force, you will multiply them and you will calculate torque. This is torque. Force times lever arm. Yeah, this is all, in fact, how to calculate torque. But these forces are acting on the object perpendicular. Look at that. This angle is 90. This angle, 90. That angle, 90. If it is acting on the object perpendicularly, lever arm is easy. Easy to draw. Draw a line from axis of rotation until where the force acts. This is lever arm. But what if the force is not acting perpendicular to object? What if a force acting like this or like that? What should we do? We have to read the definition, and once it's in the definition, we have to draw it. For example, I don't go next place, but let's draw a linear arm for any force acting on the one. Let's say that this is the force, not that one. That's F2. Draw the linear arm for F2. First, draw a line along the force. Draw it long. Second, start a line from axis of rotation here. Draw to this green line, but it must be perpendicular. Not like this. This is angle 90. Not like this. This is angle 90. You have to draw a line which is 90 degrees to this green line. It's going to be this. Almost 90, correct? So what is the linear arm for that force? This green, this line. This is the method how we draw the linear arm. Draw a line along the force, then start from axis of rotation, draw a perpendicular distance to that line. It is the linear arm. Let's apply to this the example in our book. It was this. So as you see, this force is not acting perpendicular to the range. It's acting at some angles. If the force was like this, it was easy. Say that force is this. Then force is acting perpendicularly. The linear arm is going to be D. Because D is perpendicular. Starting from axis of rotation until a line along the force. But now, given force is not this. Given force is that. It's not perpendicular to the range. It makes some angle between the force and distance. So now I need to draw the linear arm. Why? Because I know that torque equals to force times linear arm. So let me draw first linear arm. Where is the linear arm? I put a question about this in the test paper, but we met that. So draw a line along the force. This is the rule. Draw it. Then start a line from axis of rotation where the line is and draw it perpendicular to this one. So this is vertical. If you want to draw a line to the vertical, it must be horizontal. Because horizontal and vertical perpendicular to each other. So I will do that. This angle is 90. This is linear arm. Then, if I want to calculate the torque for this force, what I have to do? I have to multiply force by linear arm. But I should calculate it. This linear arm is not T. This angle is theta. That angle is also theta. So, this is hypotenuse of this right angle triangle. This opposite perpendicular leg, according to the given triangle, opposite perpendicular leg is calculated by hypotenuse times sin theta. So linear arm is going to be d sine theta. Then multiply that. Torque is equal to force times linear arm. And force is F, linear arm is d sine theta. F d sine theta is the equation. According to this equation, torque depends on three parameters. One of them is how much force acts on the object. Yeah, if the force increases, torque increases. Negative. If you are unable to rotate something, you will call someone else stronger. I cannot rotate it. Can you help me? So someone is coming and trying because his force is more force produces greater torque. Or second one, make it distance longer. Negative. Why do we use range? Because they have a long distance. When you make the distance longer, you can increase. Then you can easily rotate the object. That's why we are using those simple machines. Or make angle 90. Angle 90. Why 90? Because at angle 90, sine theta is 1. Maximum value. So sine function cannot get that value greater than 1. Then we say that The closer the angle to the 90 degrees, the greater the torque is. So when you accidentally, something happens, if you need to rotate something, what should you do? You have to pull it perpendicularly, because you produce the most torque at angle of 90 degrees. Farthest distance, perpendicularly. You have to push it and then produce the greatest torque. Okay, this was one of the examples. How does the length of the peripheral bicycle affect the amount of torque applied to the front wheel? Amount of torque depends on three parameters we just learned. F, D, theta. So in here, it's me. First time I tried it. The question is, not asking about it before. It's asking about the pedal arm. What is pedal arm? Pedal arm is the distance where you press with your foot from this pedal until the axis of rotation, which is D, what we say D. Angle is 90 because you push it down. So if you make this distance longer, which is pedal arm longer, what happens? If the increase, what happens? Torque is equal to Ft sine theta. If T increases, torque increases proportionally. Which means if you make the pedal arm longer, torque is going to be greater. If pedal arm is shorter, torque is smaller. Okay, this is one of the mystery questions. A SI unit of torque is Newton meter. I told you that, be careful about this. Newton meter is not the same as work. In the work, Newton meter is equal to Joule, but this is not equal to Joule, know this. It's a vector quantity, yes. Some torque force causes a clockwise rotation, some causes counterclockwise rotation. So, counterclockwise rotation, positive clockwise rotation is going to be negative torque. Example. Which of these forces acting on the road in the figure will produce a torque about the axis at the left hand? So, which one produces torque? What should you do? First check it. Are these forces acting on extra rotation? Extra rotation, no. Then test it. One method is left. Draw line along the force. Extend it. See if it passes through the axis of rotation. Let's see it. I will draw a line. Okay. Draw a line along the force. Let's take F1 first. Extend F1. It passes through the axis of rotation. That's why F1 cannot produce a torque. No torque. But extend F2. Is it passing through the axis of rotation? No. That's why F2 produces a torque. What about F3? Produce a torque? Draw a line along the force, extend it. Is it passing through the axis of rotation? So it produces torque. Big or small? It produces torque. Okay? And such questions are mystery questions. They are asking without calculations which force produces torque, which one not. So this problem you saw some of them. And a question about how to calculate the torque. Example, practice problem. A simple pendulum consists of 3 kilogram point mass hanging at the end of 2 meter long light string that is connected to a pivot point. Pivot point is a fixed point you are going to attach the rope. Calculate the magnitude of the torque due to force of gravity around this pivot point when string makes an angle of 5 degrees. So when you suspend the string from a fixed point, this is fixed pivot, string will stay in vertical in the pendulum. Yeah, it's going to be vertical like that. This is the natural position of the pendulum. Question says that pull this pendulum from this position, make it an angle of 5 degrees with the vertical line. Now it's going to be this way. This angle is going to be, according to the question, 5 degrees. How much torque is produced by the force of gravity? Find this. What is magnitude? Because when it says magnitude, we don't care. Rotation is clockwise or counterclockwise, because answers must be given positive if it says magnitude. So two forces acting on the pendulum's bob. One of them is gravitational force Fg. Second one is tension force Ft. Why question is only asking for separate? Because tension force does not produce a torque. Because its extension is passing through axis of rotation. Look at that. Torque of tension is 0. Torque of Fg. Let's calculate it. How much is actually the spine piece? First, F is calculated by mass times gravity, mg. M is 2 kilograms, not 3 kilograms, sorry. 9.81. It was 29.7. It was like this, 29.7 Newton. I know the force. To calculate the magnitude of the force, what I need to know? Torque must be known, so F must be known, D must be known, angle theta must be known. Force is known. 29.7. What about distance? What is distance? Draw a line from where the force acts until axis of rotation. This line is distance. It is the length of the string. D is equal to L. How much is length of the string given? 2 meters. So distance is 2 meters times sine of angle theta. So we are going to take the angle between the distance line and force line. I said I'm draw a line along the distance. Yeah, this is distance, huh? Draw a line along the distance. Draw a line along the force. Take the angle between them. Then there's this. This angle and that angle are equal angles. This is also 5 degrees. Why? In mathematics, if there are two parallel lines, two vertical parallel lines, just one single line crosses that line, these two angles are equal to each other. Two are vertical, one line crosses them, that's why whatever this angle is, that is the same angle. 5. Now write 5 there. Multiply them all, find the magnitude. I think it was 5.2. Okay. This is how we calculate magnitude of the torque. What if there are more than one torque? We have to add them to find that torque. So, a good example. How many forces are there acting on this bicycle wheel? 2 forces. I will calculate torque of each force, and after that I am going to find the net torque by adding them. But in this question, only problem is angle. Question says that each force is 6 Newton. Yeah, this is 6. This is 6. Angle between them is how much? 60 degrees. Calculate the net torque. And when I check that F1 is acting perpendicular, tangent to the wheel, which is perpendicular to radius. Axis of rotation is in here. So it's very easy. This is axis of rotation. This is where the force is acting. Then I can find easily F1 torque. Torque of F1. F1 is 6 Newton. So torque 1 I am going to say equal to positive or negative. First I have to check this. If the rotation of the force is clockwise, negative. Counterclockwise, positive. But how can I know it? We will check what is the axis of rotation. Axis of rotation is on the left. Use your left hand because axis of rotation is on the left. Hold your pen from left hand. Then from right hand, push your pen in the direction of the force. My pen rotates counter clockwise. So it produces a positive torque. At this angle is how much angle between the force and distance? 90. Why? Because it's perpendicular to radius. And the lever arm. This reduces lever arm. Find it 6 times. Lever arm is how much? It's the radius of the bicycle that's given as 1 meter, I think. Multiply them. Result is positive 6 Newton meter. This is torque produced by F1 and F2, a little different. So F2 is also acting same point. Exerted same point. Distance is the same because distance is going to be length from axial rotation until where the force is acting. What is torque? Let's find this. F2 is 6. Torque by time F2 produces positive or negative torque. Let's check it. Where is the axial rotation? On the left. Use your left hand. Hold for a moment on the left hand. Push your pen from the right end in the direction of the force. So it rotates. Again, counterclockwise, so positive. Then calculate torque 2. Positive. How much is force? 6. How much is distance from force to axial rotation? Again, 1 reduce on the bicycle wheel. What is the angle? That's the problem. This 60 degree is not the angle which we are going to use. Why? I have to draw a line along the force. I have to draw along the distance. I have to take the angle between them. This angle is not 60. But how much? This is 90. We have subtract 60 from 90. It's going to be angle is 30. So then I will write in here 30. Result, torque 2 is going to be positive 3 Newton meter. Then net torque, sum of them. 6 plus 3, result is going to be 9 Newton meter. This is a few minutes time to ask me this question. Similarly, how many forces are there? 3 forces. Calculate the torque about this point O. It's asking. One of the forces never produces torque. Which one? Torque lifting cannot produce torque because it's acting where? Axial rotation. Other forces, they produce torque. Let's check it. Extend them. 25 produces a torque? Yes, as you see, extension is not specific to axial rotation. What about 10? It also produces torque. This one is easy. Force is given, distance is known, angle is the correct angle, the given angle is the correct angle between the distance line and force line. We are just going to see it cause a clockwise rotation, which is negative, and you will find it. The other one is a bit different. Otherwise, angle is not the angle which we are going to use. Okay, first, draw a line along the distance. This is distance, huh? Draw a line along the force. This is the force line. Take the angle between them. Not that. This angle is 90. One of them is horizontal, the other one is vertical. 90 minus 31, 15. 9 degrees. We are going to use 59 degrees for this. And direction of rotation. Where is the axial rotation? On the left. Hold your pen from left and push your other end in the direction of the force. Counterclockwise, yani. After that, you are going to add them all to find the net torque. And the car torque. Remember, we said that until now we didn't talk about if you are able to rotate an object or not. We just talk about how much torque you produce. And sometimes the force you produce is not enough to rotate the object. For example, nuts. When you try to rotate the nut on the wheel of your car, can you turn it? Can you make it rotate? No, you cannot. Which means your torque is not enough. But what's causing this? What's the reason that your torque is not enough? Because there is a friction. Friction also produces oppositely directed torque, which we named as counteracting torque. Yani when you try to get something in reality, because the torque is in contact with some other surfaces, there is friction force, and friction force produces oppositely directed torque. If your torque is not greater, slightly greater than the friction torque, you cannot rotate it. But your torque must be a little greater than that, you can make it rotating. That's why we say that if applied torque by your hand is equal to counteracting torque's maximum value, object is ready to rotate. But slightly more object will start rotating and it will accelerate in section 3. We talked about this. Remember section 3? Torque net is equal to I times. If there is some net torque, what's happening? Acceleration. It starts rotating. So this is what we are going to study in this section. Required. Yani minimum torque which starts rotation is required torque. And this number changes from surface to surface, from object to object. For example, to rotate a knob is not very easy. You need a very big torque to start rotation. Because friction produces very big torque. Why? Because it's so tight. Surfaces push each other so strongly, the effect is so big. But for a door, it's not that big. For a window, very small. But every object has, because of the friction, every object must have some counteracting torque. By using oil, what are we doing? We are decreasing this friction and then we are decreasing counteracting. That's why when you do not oil the door so frequently, for many years later, it is not easy to rotate. But when you put some oil, you decrease the friction, and you decrease the counteracting torque, and it becomes easier to rotate it. Okay. So, about this, there is a few problems. One of them is this one. If the torque required to loosen a nut on the wheel of a car has a magnitude 40 Nm, what is the minimum force? What minimum force must be exerted by the mechanic at the end of 30 cm range? You should produce the 40 Newton torque to start the rotation of this nut. This number is minimum. If you do more than that, then if you are strong, do it. But the question is not asking about it. What minimum force is needed? You are not going to waste your force. What minimum force is needed? The question is this. So I'm going to use torque equation, Ft sine theta. So F minimum is the question. So that's why I had to write an equation for F minimum. F minimum is going to be transfer d sine theta to the left side. It becomes torque divided by d sine theta. This torque is a constant number given in the question. So I cannot make a change in this. Minimum force, minimum torque. But I can make a change in d and theta. D, if I want F minimum, D must be maximum. What does it mean? Hold your hand not close to the extremitation. Move your hand as far as possible from the extremitation. Make distance, longest distance. What is longest distance? 30 centimeters, because no longer than that. And make sine theta maximum. Sine theta maximum. Maximum value of sine theta is 1. At what angle? 90. So if you add the force at 90 degrees, so at the farthest distance from the extra rotation, you are going to produce torque with the minimum force. Then we are going to find how much is at minimum in this question. All are given. 41 is the torque. D is 0.3. Sine theta is going to be 1 plus sine 90. You will find answer at 123.3. About this, we have one more question. How would the force to rotate the door changes if you put the handle in the middle of the door? So, is there a friction? Yes, friction produces counteracting torque. So your torque must be minimum equal to that torque. So this is a specific number for that torque. It doesn't change. If you want to rotate the door, you should produce this. We should put whatever one. A child, if you want to rotate it, you should produce that torque first. So initially, the handle is at the end, farthest distance from extra rotation. So torque produced by F times from force to the extra rotation distance. But later you take this handle from end to the middle like that. If you take it to the middle, distance becomes d over 2 middle. Now this is t, e, this is d over 2. Then you should produce the same torque again by the force. So if distance is halved, if you want to get the same torque, force must be doubled. Then these two will cancel, you will get the same number again. If distance is decreased by 3, 1/3 of the initial one, force must be 3 bonds. Just please go through the way you will get the same answer. If distances change by 2 over 3 of the initial distance, force must be changed 3 over 2. So they must cancel, you should get the same. In this type of question, this is the answer. Yani, whatever the change factor of force or distance, force is going to be Philip version.